Good afternoon. Yes, welcome to today's lecture. I've already recorded a recap on Kirchhoff current law and Kirchhoff's voltage law. So you'll take a look at them. They'll be part of the recorded videos or recorded lectures below this particular big blue button session named KCL and KVL. So it's a demonstration of how the loops, the laws are applied in a loop structure to be able to solve complex circuits that you cannot easily determine whether they are, you cannot easily determine whether they have parallel connections or series connections. So therefore it means you go the way of the Kirchhoff rules to be able to dismantle such complex circuits. Okay. So we're going to look at capacitance as the next component. And once we finish that, we can move to theories of semiconductor. The concept of inductors, I'll post some notes you have a look at, because those three devices move together. Capacitors, resistors, and inductors, they all move together. So once you know how to work with one of them, or how to get the quantities of one of them, then you can easily be able to calculate other quantities for other related components. Okay. So we're going to look at capacitor and capacitors. Remember, I'd mentioned capacitor as a device when we were looking at electrical theory. So we know what it is, we know how it's constructed, we know the types of capacitors that exist, and of course we know what comes in for capacitors. Okay. So this recorded, you can view it under the lesson for later on, for those maybe who are not able to join. The system had issues, and I think it has been rectified, though not sure if it's very stable today, but the recordings will be available. That's an assurance that I can give out. Yes, so we can move to capacitors.
Capital F. Now, a farad of capacitance is very large. So in most cases, you will probably see references to a microfarad. And how does a capacitor work? Well, you have a capacitor which is essentially just two parallel plates connected in a circuit with a battery. And what actually happens? The electrons from this side of the battery will flow to this side of the capacitance and give it a negative charge. That negative charge, which is building up on this side of the capacitance, will repel the negative charge on this side, and that will go towards the positive side of the battery. And if it repels the negative charge on this side, it will leave behind a positive charge on that side. It's important to notice that no current flows across the gap. It's simply that the electrons flow up to this side and accumulate on that plate, making it negatively charged. That negative charge repels electrons from this side that then go back to the positive side of the battery, leaving a positive charge on this side of the plate. And at that point, the capacitor is said to be charged. How do you make a capacitor? Well, as I've said, they are two parallel plates, usually of some kind of metal foil, which are close together. And they mustn't touch, obviously, there has to be a gap between them. So what is usually done is some kind of insulator, we call it a dielectric, but an insulator that doesn't carry current will go between them, sandwiched between them, and then you roll the whole thing up, rather like a Swiss roll, and that is then packaged as a capacitor. Now let's do a little experiment. Here's the capacitor, and we're going to put a switch in the circuit. We have a battery. We're going to have a variable resistance. We're going to have an ammeter, which will measure the current flowing. And we're also going to put in a voltmeter, which will measure the potential difference across the capacitor. Now, ordinarily, if this resistance were not here, and you close the switch, then the electrons flow around the circuit onto this side of the capacitor, just as they did up here, and they will repel electrons from that side, and you will get plus and minus that side, plus on that side. Of course, initially, a lot of electrons will flow, but as the electrons build up on this plate, so they will also have the effect of repelling any more electrons coming this way. So what you find is that when you first switch the circuit on, there's a high current as electrons flow onto the plate, but that current will gradually reduce as the electrons get more and more accumulated on this side of the plate, because they then repel any more electrons from coming and make it harder for them to come. So the current will vary. And what we can do, therefore, with this variable resistor is to change it so that as the capacitor is charging, the current remains the same. So you need to start off with a high resistance to have a low current. And then as the current would naturally fall, you change the resistance and make it smaller so that you get effectively the same current being maintained in the circuit until the capacitor is fully charged. And if you do that, then you can measure the current against the voltage. And because we have set it so that the current remains at a constant level, time. So let me just recap. As the capacitor is being charged, you measure the voltage across the capacitor at regular time intervals. And what you find is that the capacitor will increase its voltage as time increases. So it's time against voltage. But we know that charge is current times time, because current is effectively the amount of charge moved in a unit time. So if the current is held steady, which is the whole point of this variable resistor, then we can say that this is also a measure of charge, because charge equals IT, and I is constant. So T is effectively proportional directly to the charge. So this is not only a measure of time, it's also a measure of charge, because the current we've kept constant. And since we started off this whole thing with a definition of capacitance as charge divided by voltage, so we're saying capacitance equals charge divided by voltage, that means that charge is the voltage times the capacitance. And that means that if you plot Q against V, the gradient of that line will be C. So that's the way you can capacitance. Now let's consider two capacitors in parallel. Here's a battery. Here's our first capacitor. And here's our second capacitor. And they are in parallel. It's a bit like in the electricity series of videos where we had resistances in parallel. What we want to know is, what is the effective resistance of those two in parallel? Suppose they were inside a box and you didn't know what was inside the box except you knew there was some kind of capacitor. What would be the effective capacitance of that box that you couldn't see inside? Well, we know that charge is voltage times capacitance. So for the individual capacitors, let's call this C1 and this C2, and the total voltage across them is the voltage of the battery, that's V, then we can say the total charge on these two capacitors is V times C1 plus V times C2. And that equals the total charge on the effective capacitor, which is essentially V times C effective. Now, of course, the V's just cancel out, and you find that the effective capacitance equals C1 plus C2. And that's the effect of two capacitors in parallel. You simply add the two capacitors' values together. Contrast that with resistances in parallel, where you would have had 1 over R effective equals 1 over R1 plus 1 over R2. Well, what about what happens if they are in series? Here is the battery. Here is capacitor 1, 2. And once again, we're imagining that this is a box, and we know there's some kind of capacitance arrangement in it. What is the effective capacitance? Once again, the battery has a value V, and that voltage will be dropped across the first capacitor, value V1, and across the second capacitor, value V2. And we know that V equals V1 plus V2. But we also know that Q equals V over C, which means Q equals VC, which means that V is Q over C. So V equals Q over C. So this V here is Q over C effective, where that is the effective capacitor of the capacitance of these two combined. Equals V1. Well, what's V1? That is Q over C1. What is V2? That is Q over C2. And now we can divide by Q, and we get that 1 over C effective equals 1 over C1 plus 1 over C2. And that is the way you calculate the effective capacitance for two capacitors in series. Now we want to talk about the amount of energy that's stored in a capacitor. Let's take a circuit where we have a couple of batteries. This is a little light bulb. Here is our capacitor, C, and here is a switch, which we can switch either way. To start with, we're going to switch it that way, so that effectively the capacitor will charge. And of course, what you will find is that that side of the capacitor will be negative, and that side of the capacitor will be positively charged. Now, if you now break that switch, the capacitor remains charged. There is no circuit, no current can flow. But it has, as it were, potential energy in it, because it's got a charge of electrons on one side and, as it were, a deficit of electrons on the other side. And if you now connect the switch that way, so that this circuit is now complete, that capacitor will discharge through that light bulb, and the light bulb will flash. It's one of the principles of the way that a flash bulb works in a camera. So just to recap, when the switch is in this direction, then the battery charges the capacitor. When the switch is in this direction, then the capacitor discharges through the bulb and produces a flash of light. And that means that the capacitor had stored energy, because that energy was what causes the light bulb to flash. What is the energy that is stored? Well, we know by definition that capacitance is charge divided by voltage. So if you've got a fixed capacitor with a fixed capacitance, if that is going to be standard because it's a single capacitor, what it means is that as the charge increases, or rather as the voltage increases, so the charge on the capacitor increases. if you were to plot the voltage against the charge, you'd find that was a straight line. And let's suppose that the voltage of the battery was here. That means that the maximum charge on the capacitor will be here. What is the energy that is stored on that capacitor? The answer is it is the area here. And what is that area there? Well, that is simply the area of a triangle, which is half the base times the height. So the energy is half the base, which is Q, times the height, which is V. And so now we have a formula for the energy stored in a capacitor. It's half the base times the height, half QV. But since C equals Q over V, you can rearrange this formula so that the energy is equal to a half CV squared, because we simply say Q is CV, and if you put CV in here, you get CV times V, which is CV squared. And it's also equal to Q squared over 2C, because if you substitute for V, V equals Q over C, so Q times Q over C is Q squared over C, and then the half Q squared over 2C. What determines the magnitude of the capacitance? Well, the first thing is the distance between the two plates, D. And the capacitance increases as the distance between them decreases. That is to say that C is proportional to 1 over D. If you make the distance between the plates smaller, the capacitance increases. The capacitance is also a function of the area of overlap of the two plates. If you don't overlap them completely, then it's only that area that determines the capacitance. So the capacitance is also proportional to the area of overlap. And finally, the capacitance is dependent on the dielectric. You remember I said that there was an insulator that we put as effectively the sandwich between the two plates. And we say that the capacitance is proportional to the dielectric, which we represent with the symbol epsilon. So we can now write our formula for a capacitor. Capacitor equals epsilon A over D, representing the three dependencies for the value of a capacitor. Now let's just think again about how we charge a capacitor. Here we have a couple of batteries. We put a resistance in the circuit. Here is our capacitor. Here we have an ammeter to read the current that's flowing in the circuit. And here we have a voltmeter to measure the voltage across the capacitor. Now, as the capacitor charges, of course, the electrons will flow around here, and this side will be negative, this side will be positive. But as we've already discussed, what happens is that initially there's a high current, but as the electrons accumulate on this side of the capacitor, they will tend to deter further electrons from coming. And so the current will actually go smaller as time progresses. And what that means is that the charge building up on the capacitor initially builds up at a high rate, but then tapers off. So that if we plot charge against time, what we will find is that it will start by going up very quickly. Charge is VC. And so if this is a measure of charge, then since the capacitance is constant, this is also a measure of voltage. So you could also have measured voltage along there, and that gives you an indication of the charge. So in other words, this voltmeter will show a sudden increase in voltage, but then it will ease off until it's level. And that will be the level of the voltage of the battery. You cannot get a higher voltage than the voltage of the battery. And at that point, no more charge will flow. On the other hand, it will ease off until it's level, and that will be the level of the voltage of the battery. You cannot get a higher voltage than the voltage of the battery, and at that point no more charge will flow. On the other hand, if you discharge the capacitor, then you'll see what's happening. If you look at charge against time, when you discharge, then it discharges like this. And once again, since Q equals VC, this is also a proxy, as it were, for voltage. So let's now look at a capacitor that is being both charged and discharged. First of all, we're going to plot voltage, which of course is also a measure of charge, against time. We remember that V equals QC, and therefore for a constant capacitance, as the voltage increases, so the charge increases. So this is both a measure of voltage or charge. And we said that as the capacitor charges up, the voltage or the charge goes up according to in time, in this way, until it is completely charged. And that's when it is at the voltage of the battery. And then we said if you discharge it, it discharges like that. And what you find is that the formula that governs this part of the process is that the voltage equals 1 minus V0, where V0 is the voltage of the battery, times e to the minus t over RC, where you remember we had a resistance in the circuit and a capacitor. Well, t over RC is the time constant. So the voltage that is measured across the capacitor as it is being charged equals 1 minus the voltage of the battery times e to the minus t, where t is the time here, divided by RC, where R and C are the resistance and the capacitance in the circuit. By contrast, the formula that dictates that fall is that the voltage measured across the capacitor as it is discharging is equal to V0, which is the voltage of the battery, times e to the minus t over RC. Again, it's the time divided by the resistance and the capacitance in the circuit. And we call the time constant, which is often given tau, as RC. Now, what happens if T in our formulae here equals tau, which means it equals RC? Well, in the case of the discharge, you can see that V would equal V0 times e to the, well, minus t over t is minus 1 because RC is t. So minus t over t is minus 1, which means that V divided by V0 equals 1 over e. And that's approximately 0.37. What that means is that in tau seconds, where tau, of course, is value RC, in tau seconds, V falls to 37% of the value of V0. And because V equals QC, if V falls to 37% of the value, then since C is constant, Q also falls to 37% of the value of Q0, which is the total charge when the capacitance is fully charged. You can also show that tau is the time that it takes for the capacitor to charge to 63% of its total charge. In other words, tau is the time it will take for this process to get to charging to 63%. 63%, of course, is just 100% minus 37% of total charge that it's going to get when it is at its maximum charge. Now you can see that since tau equals RC, and C is obviously a constant because it's the capacitor we're looking at, if you increase R, you will increase tau. And that will take it longer for the capacitor to charge, but it will also, it will take longer for the capacitor to charge, but it will also take longer for the capacitor to discharge. And that means that you can get a current flowing for a longer time, albeit, of course, it will be a much smaller current because you've got a higher resistance in the circuit, but you can get a current flowing for a longer time if you have a higher resistance in the circuit.
So we have an example there. On how to calculate the total capacitance of capacitors that are arranged in combination of parallel and series processes. So if that circuit, we have a circuit of that nature, then what we need to do is to decompose that structure or decompose that circuit. Okay, we need to decompose that circuit so that we can be able to determine which values or which capacitors are in series and which capacitors are in parallel. You can as well rearrange it so that you have smaller circuits, just the same way it has been identified in the diagram, where we have A, B, and C circuits, those smaller circuits that you can be able to handle. So if you want to compute the total capacitance in this circuit, based on the formula that has been derived previously, we know what you do when capacitors are in series, and you know what we do when the capacitors are in parallel from the previous video that was playing there. Okay, so if that is the scenario, then you just need to identify which ones are in series and which ones are in parallel. So in our case, if you want to get the total capacitance in this series or in this circuit, then we can begin by looking at the smaller circuits. So we can look at A, circuit A, and determine what's the relationship between C2 and C3. What's the relationship between C2 and C3? What is the relationship between C4 and C5 in circuit B and C6 and C7 in circuit C? Okay, so we'll obtain those smaller capacitance first before we can be able to analyze the whole circuit there. So from there, you can see the computation there. CA is 5 microfarads, and we said from the video that you just watched, you realize that farads are very large units of measure, and those capacitance that are measured in farads are unlikely to be found in most of our devices or electronic devices that we use. So therefore, we use smaller units, just the same way resistors and others will work. We use smaller units of measure in terms of the microfarads, microcoulombs, and so on and so forth. So you can see the estimation. CB is 7. So that is circuit B. Circuit C is 3. Then you can combine them together. You can combine them together. So I hope you're doing it also from your side as part of the notes that you are taking through. Okay, so we have that circuit and we have that circuit. So once you compute them, these will be around, these will be 5. That will be 3. And that would be 7. Can you confirm if you can see my markings? I'm trying to mark to show some, do some explanation using a marker, so you can confirm if you can be able to see what I'm marking. So once that arrangement is done, then you can now ask yourself, what other relationship exists between these devices? What other relationship exists within these devices? So our circuit will look like this. So we'll have circuit A there with the capacitor 3 and 2. Okay, capacitor 3 and 2. Then we'll have capacitor 3 and 4 under circuit B here. But in between here, we'll have, circuit C with capacitor 6 and 7 here. Okay. So in that scenario, still we cannot be able to solve out that circuit. Still we cannot be able to solve that circuit. And therefore it means we still need to reduce our circuit further. So what we can do, we can work with circuit A. Okay, we can work with circuit A and circuit C and see how to merge them together. And because you can see that looking at them either way around, from any direction, they are not in series. Okay, they are not in series because there's a junction there. So definitely, once this junction is here, then capacitor C is definitely in parallel with others. Okay, capacitor C is definitely in parallel with the others. So you can decide whether to merge it with circuit A or circuit B moving forward. Okay, so if you look at the computation here, it's been merged here to give what we call circuit C, D. Okay, it has been merged there to give what we call circuit D, which is going to read about 8 microfarads. Okay, then now from there, you'll definitely have a circuit that will look like this. So we have circuit D here. Then we'll have the other circuit, which was circuit B, somewhere there. Okay. Which was circuit B somewhere there. Okay. Then you'll have the others, which was, for instance, we had a capacitor here, which was capacitor 1 at about 5 microfarads. Okay. Then now the 3, this one and this one and this one, you can put them together. So they're in series. So if they're in series, then our computation should pick this particular format. Okay. Then once you compute that, you can be able to arrive at the required answer. You can be able to arrive at the required answer. Then you can estimate charge. The second question says that compute the charge of each capacitor. Compute the charge of each capacitor. Compute the charge of each capacitor. So you can see how the charge is being computed there. Initially, we mentioned that charge is CV. Okay, charge is CV. So you can compute, look for your V and look for your C, the capacitance of the capacitor and the voltage drops across that particular capacitor. What you should be very careful with, is when now you're looking at the charge of capacitors that are connected in series or in parallel with one another. So like for instance, if you look at the circuit, looking at circuit A, we have to get to know the amount of voltage that we'll experience in that particular circuit. Okay, we'll have to know. So 72 farads, coulombs, 72 coulombs should represent the original the whole circuit, or rather we can as well say capacitor 1, because it will experience the whole charge of the circuit. Okay, it will experience the whole charge of the circuit. So in other words, 72.67 is the whole charge of the whole circuit. We're using the total capacitance of the circuit and the voltage that is flowing in that particular circuit. Okay, so that is the whole circuit that we are looking down into. But now the rest, you will have to relook further. Okay, you will have to relook further and find the exact voltage that is going into that particular circuit. So how do we get the voltage that is going through circuit A? How do we get the voltage? The voltage that is going through circuit A. If we know the charge of the circuit and we know the capacitance of the circuit, then from Q is equals to CV, then V is Q over C. We can compute that, and that's where we are getting our 14.5. That's where we're getting our 14.5. For circuit B, the same approach, that's where we're getting our 10.38. Okay. So from there, you can analyze your circuit one by one and be able to determine C2, C3, what is the charge? What is the charge for that particular capacitor? Okay. So that's the computation we are doing there. There's a computation we are doing there. So using the voltage per circuit, And if you look at the values of the charges per capacitor, per circuit should always add up to approximately the original charge of the circuit. That was 72.6, about thereabout, or just 72, or something 70 and above is actually allowed in electronics, because we are not dealing with human life. Our margin of error is a little bit bigger. So 70 going forward, or something between 69 to 72 is allowed. You can be able to get your values from there. But now, per circuit, the total coulombs of charge must reflect the original value of charge for our circuit. Okay. So if you check the examples there, that's what is being calculated there. If you check the examples there, that's what's being calculated there. Q4, Q5, Q3, Q2. Okay. So the same concept is with C6, not C6, but Q6 and Q7. So first of all, determine that. Okay, so that is what the computation of capacitors is all about. Energy stored was talked to, and you can still be able to remember the amount of energy stored. And the relationship between charging and discharging of a capacitor. Most importantly is basically to know the energy stored in a capacitor, the timing of how long the capacitor is going to charge or discharge, and of course trying to regulate the amount of current that is flowing through is a discussion for another level. Okay, is a discussion for another level. So it was also the video also mentioned on what we call the geometric properties of a capacitor, the permittivity of free space, issues of area, the plates and distance between the plates. Can also determine the amount of capacitance a capacitor will be able to provide. Okay, the amount of capacitance a capacitor will be able to provide can also be determined by the geometrical properties of that particular capacitor. So now that is what the industry manufacturers use. Okay, they'll have to use the geometric properties so that they know what is the area of the plate that we need and what are the distance that we need to make so that this capacitor can be able to provide this amount of capacitance. Okay, so there's that kind of relationship that the industry are using. But now, when it comes into the market already, or it's being used for other functionalities to build up a circuit, then we use the formulas that we've talked about below here, where now we demonstrate how capacitance can be computed in relation to the arrangement that is there. Is it series or is it parallel? Okay, how many can we combine together instead of having smaller ones? Okay, combining in series or combining in parallel, which one is giving us enough capacitance to be able to support this particular circuit that we are building up? Okay, so those two scenarios interplay with one another. One of them works in the industry, in the manufacturing process of the devices. Then the other one works when we are trying to integrate these particular devices into our electronic devices for purposes of serving their functions. Okay, so that was also mentioned in the previous display or the previous explanation that was there. Okay, so I was just wrapping up what has been presented there to finish up the issue of capacitance. Okay, so I'd mentioned that before, maybe nobody was before I'd recorded a video on or a lecture on catch-off laws. I was finishing up. Remember last time we met, we did not finish up the KCVL current law and the voltage law. We did not finish up them completely. So I've recorded a lecture video that is finishing up the two and giving an explanation and an example to wrap it up so that we finish up with that. Okay. Then now what you need to do next is I want you to do exactly the same thing I've done to capacitors and resistors. Do exactly the same to inductors. Go and look at how we compute the inductance, total inductance for those inductors in parallel and in series, and what are the importance of those values? What are the importance of those total inductance that is computed in parallel, computed in series? What are the importance, and how do we make good use of that in our circuits? Okay, so go and check on that as you go for your weekend. Yes, so meanwhile, if there's any question, I'll willingly be able to address. But ensure you finish up on KCVL. That is KVL, not KCVL. KVL and KCL. Catch-off laws on current and catch-off laws on voltage. Ensure you finish up on that. The video is going to be available after we end the session. Okay. Yeah. So unless there's a question next week, I'll work on semiconductor theory. We're going to look at that is a major component of computing. Semiconductors contributed largely to computing. Issues of transistors has really revolutionized how we do computing. Issues of integrated circuits, okay, really revolutionized our way of life, how electronic devices look like in terms of size, functionality, power consumptions, and so on and so forth. Okay, so take your time, watch that video on catch-ups. You can ask questions. You can always post your questions on the forum. I'm going to create a forum there. You can always post your questions there, then we can answer some of them. Yes. Any question? Any question? Swali? Okay, so if there's no question, you can visit and discuss and have a look at the videos. Then you can post your questions on the forum.
You are currently the only person in this conference. You are currently the only person in this conference.